Oh, hi there. I didn't see you. About my hat? Oh. Well, see, I really love the game Angry Birds. In fact, I'm playing it right now. But I'm playing that new edition, the one in space. See? Now, I like this one because it has something to do with one of my favorite sciences, physics. See, in this game, you have a little asteroid you're trying to get to, and when you fling your pigs, instead of going normally like they would on Earth, they sort of follow this gravitational field here. Let me show you. There you go. Well, physics isn't really all about fun and games. In fact, this one actually has some merit though. See, though we can't see them like we can in this game, every planet, in fact almost every object, has its own gravitational field. And sometimes they do interact with each other. In fact, this is why our planets orbit and revolve around each other. Now, I think I might have some handy-dandy physics notes. The first thing that you should know about orbital mechanics and physics in space are Kepler's laws. Now, the first one says all planets orbit elliptically. This means that instead of going in a perfect circle around our sun, the Earth is slowly traveling in a small elliptical pattern. The second law says that the time it takes for the sun, for an axis starting from the sun, to go to a planet to create an area will be the same if the times are equal. This means that if this area took 3 seconds to make and this one took 3 seconds to make, they'll be the same. Now, Kepler's third law says that the square root of the period will equal the semi-major axis to the power of 3 of the orbit. Now, those three laws are very important, and sometimes they impact the lives of others, like those who work for NASA or other aeronautics companies. But that isn't everything. What you witnessed with the pig is actually somewhat of a formula. See, the force of object 1 on object 2 is going to be equal to the negative g constant of object 1 and object 2's mass divided by the radius between them squared with an r hat. Period squared is going to be equal to the radius cubed, where c is equal to 4 pi squared over the g constant times your mass. Now, your g constant is going to be in almost every formula, so it's probably handy to remember that it is 6.7 exactly. This is where the previous formula will come in. You'll substitute your c for the small equation given below, and you'll end up with your period is equal to 4 pi squared over g times m, where your g constant is right here, and this is the mass, times your r cubed. Something else that's really important when you're dealing with orbital mechanics and things in space, especially gravitational fields between them, is your gravitational potential energy. Now, this is really similar to the force of one on the other, but there are some slight differences. First, you can see that instead of two masses, or two small m's, there's one small m and one large m. And instead of being over the radius squared, it's simply over the radius. Another formula to keep in mind if you're going to launch robots up into space. You'll need to know your escape speed, or your escape velocity. See, this equation is important because without it you wouldn't be able to leave the gravitational field of a planet. Now, you can only escape a planet's gravitational field once your kinetic energy plus your gravitational potential energy equals 0. Once you have a higher velocity than what's required for that, you can leave the planet's gravitational pull. Now, the equation to find the escape speed on a given planet is equal to the square root of 2 times your gravitational constant times your mass divided by your radius. Now, this is one of the more common ones that's going to be used, but you can use the square root of 2 times g times r, and mind you that this g is not your gravitational constant. If you are going to escape the gravitational field, you need to know how to find the gravitational field. Is your formula. In this formula, g is equal to your force over your mass. But wait, because we've seen this before. Now, the equation, if you substitute your force equation for F, meaning you will substitute your gravitational constant times your two masses over your radius squared times r hat, you'll get your gravitational constant times your mass over your radius squared. Now, there's some pretty cool things that can happen when two gravitational fields interact with each other. First, there are the Kirkwood gaps. Now, these gaps occur in the asteroid belt between Jupiter and the Sun, and they occur when Jupiter slowly pulls an asteroid away from its orbit of the Sun. See, this is pretty cool because it usually only happens around exact fractions, such as 1/3, 2/5, 3/7, and 1/2 of Jupiter's orbital speed. If you look at the Lagrange points between the Sun and Jupiter, you'll find that there are a lot of asteroids hidden there. In fact, a lot that can't even escape anymore. These are known as the Trojan asteroids. Now, there is also another type of interaction between two gravitational fields in space that could actually cause a cancellation of the field. It's at these points in space that we can find such asteroids as the Trojan asteroids between the Sun and Jupiter. These points are known as Lagrange points. Now, where the Trojan asteroids are trapped are 60 degrees between the axis from the Sun to Jupiter up and 60 degrees down. So it may seem that I've gone through this rather rapidly. I will point out that it took a lot of time and a lot of people to figure out all these formulas for you so that you can find out the escape velocity of Mars or how to send a rocket up into low Earth orbit. Now that you've watched this video, I hope that you'll go out, find an example problem, and use these formulas to help you figure it out. I even hope that maybe you'll try launching your own GPS-attached camera into low Earth orbit so you can get some cool pictures of your own. In fact, now that I think about it, I even hope that your Angry Birds game gets better. Thanks for watching.